Good evening, everyone. Thank you for giving me this opportunity. Thank you to organizers and Pradeep especially for coordinating this talk. So today I'll be talking about our recent work, which was published in 2020, about IR2Vec, the way of representing programs as or way of modeling programs as distributed vectors that can be used as input to several machine learning models for diverse machine learning tasks. So let's get started. If we look at GitHub, there are more than 40 million users with more than 100 million repositories, and it's ever growing. And same applies to any other open source code hosting sites, right? Not just the code along with the relevant metadata and binaries, if they are hosted, together constitute something called as big code. If you look at the term big code, it was first coined by Reshev and others from ETH Zurich in their Popl 2015 work, which roughly denotes the availability of code on par with any big data, right? So using this code, what do we get, right? So if we manage this big code properly, they can be useful in a variety of tasks. Say we have automated tools for software engineering in one end of the spectrum. This essentially means applications like, say, similarity detection, where given two different source codes, if they are similar or not, or if they do the same job or not. And other variations like, say, code summarizations at different levels. Say it can be roughly comment generation or summarization in the form of method name predictions, or even comprehending what the whole function does, right? So and other applications include code suggestion or retrieval, something of the sort of code search engine, right? And if you look at all these tasks, they are kind of undecidable in nature, as you all know. And the other end of spectrum, we have compiler optimization applications. These applications involve optimizations like inlining, unrolling, vector factor prediction, or phase ordering, or even complex problems like register allocation or any other backend problem for that matter. Right? These problems are all NP hard, NP complete, as we all know, and they are often driven by using heuristics in any modern compilers owing to the scalability. Right. So now, how can we improve either of these stars? A common theme around all these stars is that ML, right? So ML can help in solving these better. And the next question that follows is that how to represent the code, right? For code as an input to any ML model, it is to solve these applications. We all know that in other areas like natural language processing or image processing, we have representation learning methods like Word2Vec or GLOV that tries to represent the natural language text as vectors in some n-dimensional space. Or when it comes to images, complex models like, say, CNN, or sophisticated models rather, like CNN, AlexNets, or so on and so forth, that tries to extract features from the program, features from the images for any downstream application. So do we have something equivalent to these when it comes to programs? That's the question we are trying to answer in this talk. So what we try to do is we try to represent programs as embeddings, similar to that of other embeddings from NLP or image domains. And we listed out important characteristics that could help in learning good program embeddings, or rather a good program embedding should have, right? Or these are the different cases that distinguish programs from NLP or images. So when it comes to programs, there are several languages, and programs can target several architectures. A good program embedding should be independent of these cases, and it should be able to capture semantics of the code in addition to the syntactic nature of the program. And it should be able to solve diverse applications like what we discussed, like say software engineering or compiler optimization tasks. It should also be scalable in terms of not just inference time, but also a training time. And that means we should have lightweight ML models. And more importantly, the learned embedding should not have any out of vocabulary cases. So what I mean out of vocabulary here is that, say, upon learning representations of any word, say in in NLP for English language, we learn representation for each words or each token, right? So what happens is this process results in a huge vocabulary that maps the token with a corresponding representation. So if at all during after deployment, if we are going to encounter a word or token that is not in this learned vocabulary, we'll not be able to make use of that word at all in that sentence or paragraph whatsoever. So when it comes to programs, it is important to not miss any important program constructs so that such out of vocabulary cases can be avoided, right? So yeah, this is a summary of good program representation. So now program representation, program encodings have several facets, starting with the representation in itself, and then how we make use of the representation or what kind of models we use, and finally we have the downstream applications. Right, so we let us look at the representation perspective. So first is, as very much lower in the pipeline, we have lexical tokens. These lexical tokens are the outcome of the elixir of a compiler. So we tokenize the program, and several approaches have been proposed in this area. To start with, when this domain evolved, people considered natural language token or programming language tokens on par with the natural language tokens, and used NLP techniques to process programs. And later on, people understood some shortcomings of this approach and tried to use abstract syntax tree representations, or they derived representations from abstract syntax tree, which is essentially the output of the parser of a language for performing downstream tasks. And of late, we are kind of looking at several works coming in the area of representing programs based on intermediate representations. And these intermediate representations are a nice property of being independent of source language and the target architecture, right? So IR2Vec falls in this category, and several works have come out in the recent times. And the farther end of the spectrum is is using the program dependence graph kind of analysis specific data structures like program dependence graphs that from which people have derived the embeddings. So the main crux is that when we go to completely program dependence graph kind of representation, we encode a lot of semantic information, but we tend to miss out a bit of syntactic information, which is opposite when it comes to lexical tokens. And we have intermediate representation lying in the sweet spot that captures both syntactic and semantic information to good amount of extent. Right, moving on, we have the embedding techniques, the models that can make use of these learned representation. Right, so when we have NLP-based token embeddings, we have models like word2vec or methods like word2vec that they use similar methods like word2vec rather to learn the representation. And there can be usage of non-sequential models. When I say non-sequential models, I'm talking about simpler models like fully connected networks or convolution neural networks, transformers for that matter. Or there can be sequential as well. Say if the program is modeled as sequence of instruction, then we may need to use sequential models like RNNs, LST, and so on and so forth. And if we want to learn representation out of a graph structure like program dependence graph, most common approach is to use a graph neural network like GGN and GCN and so on and so forth. And final phase that we have applications. So any of the representation learning methods can give learned representation specific for application or independent of application. Works like Code2Vec or Code2Seek, which were proposed in 2020, if I'm not wrong, or 2019 rather, they tried to learn representations for this particular task under consideration, like method name prediction or summarization. Whereas works like NCC, Float2Vec, etc., which were published quite later, focused on learning representations in a manner of independent of any of the downstream applications. Again, when we talk about applications, we have works based on several software engineering applications or compiler or HPC applications. And another flavor of this area is to generate or synthesize the code directly. So this can be code synthesis or code translation program given in one language, translate to some other language, or the natural language translated to a programming language, or programming language to so on and so forth. Right. So now, after all these background, what we are doing. So we propose IR2Vec, and this is based on LLVM IR, which makes it language and vision independent, and also makes it amenable for using program analysis techniques. And this approach is going to give out distributed representations. That means representations as a n-dimensional vector in vector in some n-dimensional space. Here, distributed encodings, meaning that the semantic meaning is distributed across the components of the vector. What this is opposed to a feature-based representation. What happens in feature-based representation is that every dimension of this vector has some specific meaning. When it comes to distributed encodings or distributed representations, the vector put together on a whole has a meaning. And finally, we follow an approach called bottom-up approach, so as to avoid out-of-vocabulary cases. That means we build our approach on a small, at an entity level, and then aggregate these representation to arrive at the representations of programs or functions, so on and so forth. We'll see these things in detail as we go along. And a bit of background on LLVM. So as we all know, LLVM's IR has is richer representation Turing complete. So this makes it a good case because it supports wide variety of front ends or different languages, and targets several different backends as well. So now we use representation learning techniques. What does a representation learning mean? It is a branch of machine learning that tries to learn representation of the underlying data automatically. So it is widely used in natural language processing. Say, a famous example is this man. If man is king, then woman is what? Then what happens is from the learned representation, we would be able to determine the corresponding equivalences is for a queen, and we would be able to retrieve the representation from the vector space. So basically, any representation learning methods helps in arriving at the representation, capturing the underlying meaning of the data. Right. So now let us start.
So when you mean, sorry to interrupt.
Sure.
When you mean automatically, is it does it come under unsupervised learning methodologies?
Yes. So what we do is there are several flavors. So basically, they are unsupervised in terms of the application. So that any application can be targeted. Yes, that's it. Yes, that is unsupervised.
Okay. Yeah. Thank you.
Sure. Okay. So what we do in IR2Vec is that we generate the IR, LLVM IR for the program, and we break this IR into something called triplets, right? So what happens here is we basically we create triplets containing relationships to relate two entities of the triplet. So we create three different relations. First is type of relation that tries to relate the opcode with its type in the current instruction. And the second relation is the next instruction relation that tries to relate the opcode of the current instruction with the opcode of the next instruction. And finally, we have arguments as a relation that just relates the opcode with n different arguments. And again, all these arguments are abstracted out. That means, like, say, all the variables are abstracted out as a single variable. All the pointers are abstracted as a pointer. Constants get a generic representation. Now, once all the statements in IR is broken down as triplets, what we do is we use a model called TransE to learn representation. What this TransE does is, say, as I just said, these triplets mean head, relation, and tail, depending on the position. And TransE tries to learn representation that satisfy this relationship of h plus r is equal to t in a vector space. At the end of training, we get a representation, n-dimensional representation for each entity that was derived from the program. And then now this becomes the vocabulary for us. We call this vocabulary as seed embedding vocabulary. And this vocabulary contains representation of each and every entity that we have seen. Now, once this, okay, so we learn this vocabulary on a good sized corpus of programs. And this is a one-time business. Once this vocabulary is learned, we would be able to use this learned representation to derive the representation for any unseen programs. Right? Say now, say for instance, if you want to represent this instruction, what we do is we just go fetch the representation of the opcode, type, and arguments, and do some sort of a linear combination to arrive at a single n-dimensional vector. So at the end of this process, every instruction would be getting a n-dimensional vector representation, which can be further processed. So this representation, we call it as symbolic representation, which is devoid of any program-specific properties, apart from next instruction, so on and so forth. We add flow information of program analysis information by modeling the problem as a data flow analysis itself. So for this, what we do is first we generate the symbolic representations. And then say, for instance, if we want to generate representation for I4 in this example, like first we will create representation by taking the representation of load, type, and all the arguments. But if we see the argument is a use of earlier definition, what we do is we make use of the representation of all its definitions conservatively to arrive at the representation for this argument. Say this J has got a definition in I2 and has got a definition in I3 and I9. So as you can see, we are not just focusing on the definitions here, but we are also looking into the memory model of LLVM IR so that whenever J is going to be tampered with, we will make use of that updated representation here. Yes, and the another point to notice here is that we are considering the definitions that can potentially reach the point. So this is a sort of reaching definition kind of a problem. And another example for I5 is here, while forming representation of I. What we do is we take the representation of I1 and we take the representation of I7. Both of these are going to change the representation of change the value of I. So now at the end of this flow analysis, we get the representations, and these representations we call as flow-aware representations. And again, here we have representation for every instruction. How we combine the representation of the instructions to arrive at function or program level or basic block level is a separate problem. It can be dependent on application or how we want to model the vectors. So several possible ways exist. So we can just simply do some sort of linear combination. If we want to give some weights to the particular instruction, more higher weightage for particular instructions, or so on and so forth, we can do some sort of linear combination, or we can put it into a machine learning model and allow it to learn these weights so as to get the representation. They can be sequential models, they can be non-sequential models, or we can use attention networks, etc. So on. So in the paper, what we proposed was a rather very simpler approach. So what we do is from the learned representation of the instructions, we derive the representations for basic block. Now, the representation for basic block are based on the instructions that are live and live at the out of the basic block. And we just did a summation of all the representation that are live to get the representation for basic block. And for function, the process is similar. Summation of all representations of basic block vectors would give a function, and similar thing happens for program. Yes, and what can we do with this vector? These vectors, again, as we have seen, there are several possible opportunities, compiler optimizations, or software engineering applications. I'll not go through this again, but just for sake of completion, I have listed it here. So now I'll talk about the experiments that we did, or experiments that are discussed in the paper. So for data collection, that means for learning the representations, the symbolic seed embedding vocabulary, what we did was we took a collection of programs from entire spec CPU 2017 benchmark suite. And we also took the programs from Boost libraries, and there were about 13,000 files, if I'm not wrong. And we converted them to LLVM IR, and all these this IR is now processed to extract the triplets. So we had an LLVM pass to extract the triplets and put it into a required format, and which was consumed by the Transy model, a standard Transy model without much changes in hyperparameters, to learn the representations. So at the end of learning, we wanted to see if we can get any meaningful representation, meaningful details captured in the representations, or can we answer similar questions like what we discussed in the beginning of the presentation when it comes to natural language processing? Can we answer such questions based on the representations that we derive from IR2Vec? So the finding was gave a lot of insights. Say we show clusters of clusters here. These are not clustered, but rather these are just projection of the learned vectors in n-dimensional space. What we observe here is that these are all floating point operations, and these are all integer operations, and these are all arguments. What it means is that all the floating point operations get a similar representation. They are put close together, and all the integer operations are fairly close together. Interesting case is here where we have a look at casting operations. As we know, LLVM IR contains integer-based casting operators and floating point-based casting operators. The casting operators that work on floats are put together with floating point operations, and those that work on integers are again put together with the integer-based operations. And this is another interesting case where a vector type is put at a roughly equidistant space in comparison to integer type, float type, or any other basic types. This also shows that vector type can take either of any of these types, basic types, as part of it. Right, and we also formulated some analogy questions and see if we can retrieve the an appropriate answer from the by using vector operations. I'll just point you to an interesting case that we had. So we were able to answer this analogy. That means if signed division is equivalent to a right shift operation, then multiplication is to what was the question that we posed. And from the learned representation, we're able to successfully retrieve left shift operation as a result. So this shows that the representations that were learned capture a lot of details in it, are able to capture intrinsic information pertaining to the operations themselves. Right. So now moving on to the experiments themselves, we had discussed a couple of experiments. One is about heterogeneous, one is called heterogeneous device mapping. So here the problem is to map a kernel to an optimal target among CPUs and GPUs. We all know that for any arbitrary kernel, GPU cannot be a de facto choice. There are kernels that perform better when we put it or run it on a CPU rather than a GPU. So this is the problem. This forms the crux of the problem. So given a kernel, determine which device to deploy it on. Right. So this is based on a famous classical paper by Groove and others, which was published in CGO in early 2013 or 2014. So this we use the same data set just to demonstrate the usability of our learned representation. So here we use a simple gradient boosting model to do classification task, and we use tenfold cross validation since the number of data points are not very much higher. So we train the model on a part of the data set and test it on other parts. So we do it across tenfold. So in order to study the generalizability of the model. So the dataset had two different GPUs, one from AMD and one from NVIDIA, quite old rather. So on this dataset, we were able to achieve highest accuracies by using both symbolic and flow-aware representations on an average across all the or most of the benchmark suits that were considered. And in terms of in speed up, again, we were able to outperform, or flow-aware embeddings outperformed almost all the earlier approaches, starting from the work of Groove himself, then DeepTune, InstaVec, or NCC, and even flow-aware is better than symbolic representation. And specific use cases here, say some kernels like embarrassingly parallel, which gives a very good performance when we map it to GPU, were mapped correctly to GPU across all turns of cross validation. And kernels like LU, that is more CPU friendly, are mapped to CPU with a very high confidence of more than 95% correctly. So that means this leads to very less slowdowns with, we are able to achieve very less slowdowns with IR2Vec predictions. And slowdowns were there in only about 20 benchmarks, and even among them, the slowdowns were within 10%. So moving on, we have a second experiment where we predict the thread coarsening factor. Thread coarsening is process of fusing two or more concurrent threads in a GPU in order to reduce the overhead. Sometimes it is not okay to have unlimited parallelism, so it is better to narrow down the number of threads to run a program. So the thread coarsening factor determines the number of threads that can be fused. And optimal thread coarsening factor varies across different architectures of GPU. So within AMD or within NVIDIA GPU, not two different GPUs can make use of same or a similar thread coarsening factor for that matter. If this factor is not tuned, the performance is going to be bad. So thread coarsening factor that gives best performance on one can give very bad performance in another architecture. So this was also based on a earlier work by Magni and others. An extension of this work was published in TACO as well. So we made use of same data set proposed by the authors. So we consider they had two GPUs from AMD and two GPUs from NVIDIA. So even here we were able to get improvements in terms of speed ups across in comparison to all the earlier approaches. And even here, flow aware representations seem to achieve higher speed ups than symbolic representations. Yes, so particular cases like SPMV and MV-call, these kernels let me just see. Yeah. So these kernels are hard to tune for the thread coarsening factor. SPMV SPMV always gives a negative performance or slowdowns in almost all the earlier works. And yes, so yeah, same applies for MV call. Here, if not tuned properly, all these would give a negative speed up or slowdowns. This is true in case of AMD device as well. Say MV call always or mostly shows negative performance in SPMV. So even in these kernels, we were able to rightly identify that the coarsening factor should be 1 in order to get optimal performance. So we didn't observe any slowdowns in these cases. So we were able to rightly map. So that's the point I want to bring it up. So we were able to achieve the best possible speedups in almost 70% of the kernels that were considered. And even here, the slowdowns were very rare. That means less than 10 cases, we observed slowdowns. And even here, slowdown is within 10% of the baseline. Okay, now let us talk about the training characteristics of IR2Vec. So IR2Vec embeddings are almost non-sequential, unlike other approaches that model the embeddings as sequential data. One important case is that if we model data in a sequential manner, we need to use a sequential models like LSTMs and RNNs. So that is one important point, and this is directly observed when it comes to training time. So in case of device mapping application, the gradient boosting model took just 5 seconds to fit the data, whereas the training time were a lot more in case of earlier works, specifically Deep Tune and MCC. This representations and the application result in greater reduction in training time, not just on device mapping, but also in thread coarsening. Even in thread coarsening, we see a similar improvement. And to compare flow aware with symbolic representations, generating flow aware representations obviously would take a bit more time because of the analysis that we do. The graph shown here corresponds to the state that was there when the paper was written. So at that time we observed more than 1.5 times time taken by flow aware representations in comparison to symbolic representations. Now we have optimized the code, optimized the algorithm using which how we derive the representations. So it should take lesser time now. And another objective that we had was about out of vocabulary cases. Now, by design, we have eliminated out of vocabulary cases by maximal amount. So this was achieved by following a bottom-up traversal. So initially itself, we decomposed the instructions into a set of entities and learn the representation of these entities, and then we accumulate these representations to build representations at higher level. Right. So what happens here is we naturally the space which we want to look at comes down drastically in comparison to other approaches that tries to learn representations at statement level. So we know that in LLVM IR, as mostly any opcode can go with any type of arguments in most of the cases. So there is the space complexity is of opcode times type times the different possible arguments. So unless during training the entire this huge space is exposed, we will not be able to avoid out of vocabulary cases, which is opposite when it comes to IR2Vec. So it is not opcode times type times argument, rather it is opcode plus types plus and number of arguments. So if we just come across a particular opcode type and argument, it is going to be in the vocabulary, and hence we'll be able to avoid out of vocabulary cases. So here on we considered some programs from programs available on net, and we studied for out of vocabulary cases. So we didn't observe any of the none of the programs that were in out of vocabulary cases. So what is the current status? So we had it accepted in TACO. It is available online, and we have a pretty much actively maintained repository which is open sourced. The code is available here. We have support for LLVM 8, 10, and 12. We are going to have a release for LLVM 14. So now we will have a release for every alternate versions of LLVM. So 14 and 16 would be released very soon. Here we make the tool available as a standalone tool. That means an executable is available that can be readily used, or it is also available as LLVM libraries. Say if you want to try it on some compiler optimizations directly linked with LLVM, the libraries can come handy. And recently we also have support added in compiler gem. Compiler gem is a very recent work which was published last year in CGO. This work tries to create infrastructure for reinforcement learning infrastructure for compiler optimization, training for compiler optimizations. So in compiler gem, we have support for IR2Vec, so you can readily make use of IR2Vec representations for representing programs there. And in the next release, we also would have a pip installable module. That means just using import IR2Vec package would give almost all the vectors that you want to access. So this is what we have in the current repo. And we did use IR2Vec representations to for some of the downstream tasks that we discussed, particularly loop distribution. This using reinforcement learning. We use reinforcement learning here for arriving at a better loop distribution sequence that would exhibit better locality and vectorization characteristics. This work is accepted very recently in LLVM HPC. It should be available online very soon. And we also tried out phase ordering, focusing on code size reduction. This work was published in ISPAS 2022. And also we did try out some form of algorithm identification when it comes to network applications. So networking devices, there are sophisticated networking devices available, programmable networking devices rather, that contains a lot of accelerators in it in addition to a generic core. So we try to recognize a particular chunk of code as particular algorithm, and once we have notion of the algorithm, we try to map it to an appropriate accelerator here. So this work was accepted in a workshop very recently. So in summary, I discussed about IR2Vec, a way of representing programs as n-dimensional vectors or embeddings by using program analysis-based representation, which is independent of language and application or even architecture. And if the representations are not data hungry, we maintain pretty much a smaller vocabulary size. And also, we didn't encounter any auto vocabulary issues due to the bottom-up approach that we discussed. It also makes it more scalable. And finally, the training time is very much lesser in comparison to other applications. Yes, thank you very much for this opportunity. That's all I had. We can discuss if you have any questions.
Yeah, thanks, Magiro, for the presentation. If anyone has questions, yeah, please unmute and ask, or type it in the chat so I can ask the speaker. So there is a question in the chat. I don't know if it was resolved. So what is the impact of removing variable removal means? Does program has one variable?
I didn't get this properly. So variable removal.
No, the question
is
is,
it
see,
about?
yeah,
Yeah.
okay. Hi, this is Ravindra. So
Hi.
what I mean is, sorry, maybe I was traveling, so I'm typing quickly. So the question is, see, if I remove variables and variables, in order to do the representation, you remove variables. Then what does it mean? I mean, in terms of, now, how do you represent variables? Because they play important role, right? I mean, if you do addition of two, now, I mean, if you have an instruction which apply on two variables and store those results, its results go into some other variable. Now, if you remove variable names, essentially you are collapsing all the operations onto a single location or whatever. Does it, how does it impact downstream application? Is one thing. And secondly, variables do carry a lot of meaning, right? I mean, right now, removing, of course, some of the software engineering tasks paramount important.
Correct.
Needs. Maybe that, anyway, that information we lose in that abstraction. So
Right.
I wanted to understand, is it like low insensitiveness kind of thing? I mean, which is across statements. If I consider statements as bad, but what does it mean by removing variable means? Is it something like some sensitivity loss or some level of abstraction?
Yeah, sure. So this is a very nice question. So what we do is we remove the names of the variables and abstract them out while learning the representations for seed embedding vocabulary. Right. So that is a one-time process, and this process is very much analogous to a pre-processing task in an NLP domain. So even there, we remove all the names, so on and so forth, in order to generate a generic representation. So it is a very similar to that. But where we bring in the notion of what variable does is in propagation of this flow sensitivity. So there we make use of this. We kind of capture the context of context of where the variable is being used and how it is being used is captured there. So if that is what you are looking for, maybe I think that kind of helps. And secondly, when we have software engineering applications, it is completely right that the variable names play a major role. So there, I think we should explicitly have the names of the variables included using some way of some representation, some natural language processing representations, and add it, or it can be some form of concatenation to these vectors in order to make out things together. So that is what that might help. if I answered the question.
Okay, thanks. I have another question. See, I'm very naive to this whole thing. So how does your representation and what does so-called this transformer buzz or, you have large language models like GPT and all. How does your stuff is different from that? I mean, your representation, I guess from using transformers also, we have some representation of programs, right? Of course, there we have, that's some kind of end task is there. Here it is, I guess, only representation, right? There we have, it's more supervised learning.
Correct. Yeah.
Right.
Right. So
I mean, sorry, maybe to ask. So, can the representation generated by your LLV IR2Vec be input to the transformers?
right. Okay. So that can be done. See, the works that you are talking about tries to they are not representation learning methods. Rather, they focus on solving a particular application. Right. Say for these models, the program is fed directly as input in some manner after pre-processing, and the transformers try to learn a way to solve the underlying task in an optimal or near optimal manner, so that this is solved. So this is a supervised learning, as you said. Rather, this approach is quite different. We try to learn the representation of the programs directly, without considering any of the downstream tasks. So it is very much similar to a word-to-vec representation. Word-to-vec is a very much of a vanilla representation for getting the representation of natural languages. And with this representation, we will be able to perform any of the downstream tasks by feeding it as input to ML models. Right. So this is also conceived in a similar thought.
Right. So in that context, whatever kind of statement I made, can, for example, for a software engineering task like summarization, can I use your representation as the representation of program and the NL description in some kind of word-to-vec representation and feed this to a transformer-like thing to learn the model?
Yes, that is very much doable. Yes.
Okay. Thanks.
Yeah, basically the objective is to capture the representation, and if we add more information to the representations while learning the representations themselves, the end ML model need not do heavy lifting for finding features or distinct context to perform the job. So if we can capture as much semantic and syntactic meaning into it, we can make the life of model or whatever the end goal much more straightforward, at least in a better way. That's the idea. Yes. So considering that, we can use this in combination with some representation of natural languages and feed it to a model to do any software engineering task. Yes.
Okay, so we also have another question from the chat. The question is, would like more insight into how we have managed to check vectorizability of programs.
So is this about the final slides that I showed? Can you please give some more details if possible?
Yeah, I think so. Yeah.
Right. So the objective there was to perform loop distribution. So if any good loop distribution would try to do better vectorization or capture better locality, right? So we try to do distribution in such a way that we get beneficial or better vectorizations. That was the idea.
Right, but how do you understand if a loop can be vectorized through the program representation.
No, the compiler will tell, right? Say we would feed the representation to an ML model, and the model would be trained with some objective. So in this case, the objective was to do distribution. And once this distribution is done, we feed the generated code to ML model, and then if we allow it to flow through O3 pipeline, we can get the vectorizability, right? If that is what we were looking for. And if the vectorization without doing our distribution, and by after doing our distribution, if it is better, or if it is going to result in improvements in performance, yeah, that is the objective.
Sorry, but I might not be correct in saying this, but is there a way that we can bypass this step totally? Like we are first sending this data to the compiler to get an idea about the vectorizability, right? Is there some way to get to know even before sending it to the compiler, like running a simple test on the program or something like that?
See, the vectorization heuristics can be checked in Python if we can offload such things to Python directly. So, but I think that needs lot of efforts. But rather getting input from compiler is more straightforward.
And also, I think the payoff will not be that significant, right?
Sorry, what will not be significant?
The time that we'll be saving by doing so will not be that much of.
Yeah, that is true. Yes. Correct. The checks would be same anywhere, irrespective of the place we do. Yeah, that is.
Thank you so much.
No problem.
So Venkata, it'll be helpful if you can provide a demo or something like that, or how do I use your toolchain or your library? Let's say I have a functioning compiler pipeline. How do I fit in your methodology?
Right. So how to use IR2Vec? I think we have a detailed description on the usage of IR2Vec here. We have also included a couple of examples here on how to use it directly in the source. This example runs you through the case of using IR2Vec as in LLVM code directly. What are the things to add in CMake list, and how do we access the vectors are described here. Now, we also provide a learned representation. The seed embedding vocabulary is also included in the repository. So you can just directly call the IR2Vec APIs, and you will be able to get the representations in a very straightforward manner. And once you have these representations, you can feed it to a model of your choice, or if you want to model it in some way, you can feed it to a model and try to use these vectors in the way you want. And also we also have the binaries available. So the binaries and libraries are in fact available in the artifacts. If I'm not wrong, you can directly try to make use of it. But yeah, it is available here. You can directly make use of it. And now we have very recently we have added some way of making it accessible. It has a Python package. So if you want to directly consume it in an ML model, which should be written in Python, so you can just directly import IR2Vec package and access these vectors. It should be very much straightforward.
Okay. Yeah, thank you. So how do I use it with compiler gem? So I haven't used it, but you know how to use it.
See, in compiler gem, what happens is for any target application, right? Say we want to optimize for phase ordering. You need to define any reinforcement learning problem. Compilism focuses on reinforcement learning problems. Like any reinforcement learning problems, you need to define your environment, define the action space, rewards, so on and so forth. Here, where IR2Vec will fit in is for representing the program. So you can generate. You'll be able to generate representations by using any of the similar works that we just discussed in the presentation. Say you will be able to get InstaVec representations, or you will be able to get program ML representations or something like that. And in addition to that, if you want to get the representations from IR2Vec, you will be able to get the representations as IR2Vec vectors. That's what I meant.
Okay. So on program ML, so I was recently looking into it, and and it also captures the flow information as well, right? So how is your method contrast with the program ML's representation?
See, if I'm not wrong, program ML doesn't capture these data flow information, but rather they try to predict the data flow information from the learned representation. That's as an application. And it's also an work based on they try to improve the InstaVec representation that I proposed earlier. These two are a bit different, if I can say so.